Hello everyone. In this meeting, we would be continuing our offline class in the online mode. So we would be discussing complexity, which we had been doing before. To do a quick review, we have discussed about problems. We talked about optimization problems, and we said that there is a polynomial time variant to an equivalent decision problem for these optimization problems. So we might as well look at the decision problems alone. Then we said that decision problems could be all brought into a common format. They could be modeled as language recognition problems. And in order to assess their hardness, we could think about the computing model, the complexity model that is used in order to find out the recognize the language, that is they recognize strings as belonging to the language or not belonging to the language is the basic idea. In that context, we had talked about the class P of problems or languages. So a class P of problems we said was a polynomial time class as popularly known, and the formal definition of that would be that a language L belongs to the class P if there exists a deciding deterministic Turing machine such when it is given an input instance encoding of called X, it would be halting with a yes if X belongs to L and halting with a no if X does not belong to L. And in either case, it would be taking time, which is given an upper bound by length of X raised to a constant. That is that many number of steps. So they are decided in polynomial time is the basic idea. We could as well have a polynomial time algorithm to solve it, which would mean an algorithm, say A, such that it takes as its input a parameter, which is the encoding of the input instance X, and in O X raised to C, a constant number of steps, it returns the answer either as a yes or a no. That was a polynomial time class. Then we talked about the intractable class, which was all problems which have only exponential time or burst solutions. So it means that every Turing machine to solve that would be halting in a lower bound 2 raised x length number of steps. In fact, it may even take a much higher time than 2 raised to x. But then every Turing machine to solve it would do that, is the idea. Then we had said that apart from all this, we could think in terms of NP. That is what can a non-deterministic Turing machine do. So we had talked about a class called NP, and the property of problems in this class or languages in this class was that there exists a non-deterministic deciding Turing machine which works in order of x raised to constant number of steps and decides a yes or a no. That is halts with a yes or no, depending on whether x belongs to L or x does not belong to L. Now we could have algorithm-based definition of I and NP as well. For I, it would be that there may not exist an algorithm or there may exist an algorithm which would be in algorithms or all algorithms, if any, to solve it would be taking a lower bound of 2 raised to x time. And for NP, it would be that we had discussed the concept of polynomial time verification. That is, there would exist an algorithm such that it takes as its input x and it also takes as its input certificate C. And the certificate C is of the length of x raised to constant, and it stops with a yes if C is a certificate to X belonging to L, which means that of course X belongs to L. And if it says a no, it means that C is not certificate to X belongs to L. So if it says a yes for an answer, one can take it that X belongs to L. But if it gives no for an answer, we can't take that. It would mean that C is not a certificate to X belonging to L. We had seen instances of polynomial type verification in some problems. Then the concept that we had talked about was many to one polynomial time reduction. Many to one polynomial time reduction. We had said about car production, and we had taken this symbol. We had said that the symbol for it looks like this, and we would say that a language L1 is polynomial time many to one reducible to L2 under certain circumstances. What was that? We had said that this would mean that there exists some f, a function f, such that f maps from sigma star to sigma star, and every x belonging to or not belonging to L1, we would be able to compute an fx in order of x raised to constant time, number of steps that is, such that x belonging to L is logically equivalent to f of x belonging to L2, which would mean that one could use the solver for L2 to solve L1. So x, if it is input, what we want to know is whether x belongs to L or not. So we would be giving x to this computational device f, the function f, which would be converting it into fx, and fx would be giving an answer yes or a no, and this answer is the same as the answer to x belongs to L1, x does not belong to L1. So it is actually the answer to fx belongs to L2. So this whole thing then becomes a solver for L1. That is the fundamental idea behind polynomial time reductions. We will see many of these reductions in this class. Now, reductions are a powerful tool for studying complexity. So we will look at some implications of reductions. Now, suppose you have that L1 is polynomial time reducible to L2, which means that you already have a function f of the type that we said. Now, suppose L1 is intractable. Intractable means that all Turing machines to solve it would be taking lower bound 2 raised to x time. Now, what would happen? Now, can we have L2 belonging to P? This is true. Just take it that this is given, this is true, or this is the truth. Can L2 belong to P is the question. Now, you may be able to infer that L2 cannot possibly belong to P. Why? If L2 belong to P, then if x belonging to L2 can be decided in fx raised to constant time, which means that x belonging to L1 can be realized in. Now the length of fx is order of length of x. So we know the order of length of x raised to some polynomial. So x raised to some polynomial constant. So constant 1, constant 2 or something we can say, which is a constant time. But we know that, so which means that L1 belongs to P. But we know that that is not true. If that is not true, it means that we have reached a contradiction. So because we have reached a contradiction, it means that L2 cannot belong to P, right? Because L1 is polynomial term reducible to L2 is true, and L1 is intractable is also true. Under the assumption that both these are true, we cannot possibly have anything other than L2 is also intractable. That is, L2 cannot belong. So that is what we can infer in this case. Now let us proceed further. What if something is reducible to a probability? So we are saying that we are again back to the same point. We are discussing another implication. So we are saying that this now is known to be belonging to P. So what does that tell us about L1? That tell about L1. L1 also will claim that L1 is P. Now, what would happen if L1 does not belong to P? Then we would say that it's outside that class. So L1 belongs to the intractable class or the hard problems that we know, all classified and put together. So if L1 belongs to I, that is, it cannot possibly have a polynomial time solution at all. If that is the case, then what would be the implication? Then it would mean that because L1 is polynomial time, if we take an x belongs to L to be solved. Now this can be converted to fx in order O x raised to c time, and then L2 can decide it fx in order of x raised to some other constant c2 time. So which would mean that x belongs to L can be decided in order of x raised to c1 plus c2 or constant time, which would mean that L1 does not belong to I. So we are saying that this gives rise to another contradiction, because we are starting from the fact that L1 belongs to I, and then we are saying that L1 does not belong to I. So it means that this possibly has to be true, because if it was not true, then contradiction. So it means that if a problem can be reduced to a polynomial time problem, then this too must be polynomial. That is the takeaway. So we have two things that we have seen. One is that if a problem can be reduced from an intractable problem, then that too must be intractable. If a problem can be reduced to a problem in P, then that too must be polynomial time. Those two are what we have seen so far. So that tells us or leads us to the direction of hardness. So this actually indicates the hardness direction. Any problem or language can be reduced to a harder problem. So because as we know, there are easy problems, but then we can always do them in a hard way. We can always convert them into a problem that is harder, right? When we solve problems by brute force, that is exactly what we are doing. We are spending much more steps on it than required, right? So this gives us the direction of hardness. So this would mean that on this side, it has to be at least as hard or harder. So L1 is polynomial time reducible to L2 means that L2 is at least as hard as L1. That is what we can infer. So with that takeaway, let us proceed. Or L1 cannot be harder than L2 is what we can infer. Now, that leads us to a class called the NP hard class. We had already discussed in class, there are a class of problems called NP problems. We had said that these NP problems mean they are polynomial time verifiable. We had said that all our P problems also are NP because if there is a deterministic Turing machine, there can be a non-deterministic Turing machine. So we had said that P is a subset of NP. And we had also said that, but P is a proper subset of NP or P is equal to NP is not known. P is a proper subset of NP would mean there are problems in the NP class which are intractable, which is not proved. P equal to NP means that all problems in NP are going to have polynomial time solutions. But then that is also not proved because there are problems in NP that people have been trying out for many years and still not got any polynomial time solutions. So only this is known. These two are unknown. They are still questions awaiting answers. So if we want to study this set of problems, we need a way by which the harder problems in NP can be taken and studied together as a group. Because it looks as if some of them are elusive, some of them are not. Those that are already in P are not elusive. We have many ways of solving them. But those that are in P but not found polynomial time solutions, yes, they are elusive. And how do we classify them? So one idea that came up was that we could have something called an NP hard class. What do we mean by that? What we mean is languages or problems that are as hard as mean it may be harder than also. Harder than all problems in NP. So then how do you get these problems? So what we want is an NP hard class which is going to help us to take out the hard problems. So what we want is something such that all NP problems would be having a polynomial time reduction to the problem L, which we would call as NP hard. So we would have to establish that all NP problems can be put as this. Okay. Now, so that is the NP hard class. So many hard problems, even intractable problems can come into this, because as we said, easy problems can always be polynomial time mapped to harder problems. So NP hard is going to contain a lot of hard problems. It is also going to contain uh, intractable problems. But those are not what we wanted to study, because what we wanted was to constrain the hardness, constrain the study to the hard problems, hard looking problems in NP, right? So in order to avoid very hard problems into this, or intractable problems, one comes up with another class of problems which is called the NP complete class. NP complete class means a problem is NP and it is NP hard. So then we rule out all the intractable problems or known intractable problems, because they are not NP. They won't have a non-deterministic derivation which is going to verify them in polynomial time. So we would be ruling out already known intractable problems. We would be also ruling out known polynomial time problems, because they won't be having a, I mean, it won't be the case that all NP problems can be polynomially reduced to this. So we can say that P known P are avoided, known I are also avoided. Known P are avoided because we want it to be NP hard. Known I are avoided because we want it to be NP. Okay. So that is the NP complete class. So NP completeness class is a very useful and very important concept, because they help us to club all the similar problems together. Those that avoid being I as well as being proved P. Okay. Those that have eluded such a proof, they all would fit in together into this class. So that class is fine in the sense that we'll see what all we can do if we know a problem to be NP complete. So if we knew that, say, problem L was, for the present don't bother, was NPC, NP complete. Suppose we know, somehow we are able to fix up that L was NPC. It has a lot of implications, right? Because now that would mean that all NP problems would have a polynomial time reduction to L, and because L is, the reason being that it is NP hard, and because it is NP, we also know that and we also know that because L is NP, so it can be polynomial time reduced to all NP hard problems. Because every NP hard problem is such that all NP problems can be polynomially reduced to it. So this is what we can infer about a problem that is NP complete. Okay. So what does that tell us? So if we have, say, another problem L dash which is also similar, then it would mean that L dash was, say, NPC. Then it would mean that L is polynomial time reducible to L dash, right? How would that come? from this path. It would also mean that L dash is polynomial time reducible to L. Reason being that all NP problems are polynomial time reducible to something in NP hard. So as both of them are NP and NP hard, both of them are polynomially reducible to each other. So that is a common property shared by the NP complete class. That is why it is also called complete. Reason being that all NPC problems can be polynomially reduced to each other. That has very good implications in the sense that suppose, as we said, L1 and L2 are two problems in NPC. Then if you make a discovery about one of them, say, so if you make a discovery that L2 is P, that is you find a discovery, because this is something great, so that's why I'm putting it as a discovery. So we find a polynomial time solution to L2. Then the implication is that L1 can also be polynomially solved. Would also get a polynomial time solution. In fact, all problems in NP would become polynomial time there. If on the other hand, suppose L1 is proved intractable, that is any problem in the NPC class. If it is proved I, that is intractable, that is it has only exponential time or higher solutions, then what is the implication? It would mean that L2 can also have only it would mean that all problems in NPC class intractable. So that is the importance of this class, and we keep on adding more and more problems to this class. The idea is that NPC problems, if one of them is solved, all the others get solved. In the sense that they get polynomial time solutions. If one of them is proved intractable, all the others would become intractable. So that's a completeness class by itself, and it makes a very, very interesting field in computer science. So we said that if we had one such known L, which is NP as well as NP hard, then it has so many implications, right? So the question is, but then how do you prove that something is NP hard? How can you possibly give a reduction? How can you prove that L is NP hard? You will have to give a reduction from all NP problems. That is our definition. And it is, as we know, it is quite difficult to do that, right? It won't be possible to work out all possible NP problems and give reductions. But the thing is that this was got done in a very ingenious manner, or rather this was discovered by not just Cook alone. It's called the Cook-Levin theorem. And they proved that one problem is NP complete, which is CNF SAT or satisfiability. NP complete. In fact, there is a big proof. We go into that proof. If we have time later, I may look for a proof from circuit satisfied rate. Circuit satisfied is an equivalent problem to CNF SAT. CNF SAT is something we have seen before in class. You may be remembering, and the false form, right? Conjunctive normal form. We have a formula, and then we have to have an assignment of literals, literal values to make f equal to 1. Whether it is possible or not with an assignment, that is the issue to be solved over there. So Cook-Levin showed that this problem is actually NP complete, which means that all problems in NP can be polynomially reduced to this problem. And it is also NP that it can be solved by a non-deterministic Turing machine in polynomial time. So because of Cook's theorem, a lot of work becomes easy in the sense that if we have to further look at more problems in this domain, we can take the CNF SAT as the basis and then work up from there. So for example, if you take the next problem, you are able to show that taking for granted that CNF SAT taking for granted that CNF SAT is, as we had seen in the last slide, CNF SAT is NPC. If we are able to show that CNF SAT can be polynomially reduced to some other problem, your problem L, then L and becomes NP hard, right? Reason being that all problems in NP are polynomially reducible to CNF SAT. So all NP problems polynomially reducible to CNF SAT, and if CNF SAT is polynomially reducible to L, then L becomes NP hard. And if we are also able to prove that L is NP, if you prove, and this is also if you prove, then L is NPC. So that is how you can add more and more problems to the NP complete class. Once you have proved about L, you can use L on the left hand side, and you can prove that to be polynomially reducible to some other problem, so that that other problem along with an NP proof, it will start belonging to NPC. So that is the way in which we are going to do things now. Okay. So you may be remembering in our class we had talked about a number of problems: click, vertex cover, independent set, coloring, etc. So some of these problems we'll be doing now in class. CNF SAT, its NPC-ness is given by I'll start the next class by from this point onwards, that is showing a reduction from CNF SAT to click. So for the present, I'm stopping this one. Please review the concepts that have been done in this before you move on to the next one, that is reduction from CNF SAT to click and a few other reductions. Please make sure you understand everything before coming to this.